Good morning to one and all present here. My name is Agni B. Nair and I'm here to present my DAA Capstone project. So the problem statement I received was 107, nicknamed Invitation the Old-Fashioned Way. So it goes like this. You are hosting a family function and must personally deliver invitations to your relatives' homes, starting each morning from your own home at the origin. You must navigate to various relatives' location and return home by the end of the day. Because the event is approaching, your objective is to complete all invitations in the fewest number of days possible. You start from your home at 8 a.m. and must return home by 6 p.m. Basically, this means I have 14 hours of window. You will spend 15 minutes at each relative's home for a visit. You travel at a constant speed of 40 units per hour. All distances between the points must be calculated using the Euclidean distance. Each relative on the list must be visited once. Goal here is to determine a multi-day itinerary that minimizes the total number of days required to visit all relatives while ensuring the time constraint and travel speeds are strictly followed. Input specifications, a set of M coordinates representing each relative's home. Output specification, daily itineraries for each day 1 to D, where D is the maximum number of days allowed. The sequence of relatives visited. Key points here in my problem scenario is that invitations must be delivered to multiple relatives. Each day starts and ends at home, which is represented by 0, 0. Each visit takes 15 minutes. The travel speed must remain constant of 40 units per hour. Must return home before 10 p.m. Goal, deliver all invitations in the minimum number of days possible. This problem becomes vehicle routing problem with time constraints. In real world, it maps to home becomes the depot, relatives becomes the customers, each day becomes the route. Travel becomes the edge distance in VRP terms. So why vehicle routing problem? VRP allows multiple routes. Each route starts and ends at the depot home. Constraints such as time limits, optimization of route grouping. Within VRP, we use Clark-Weight algorithm. Why Clark-Weight savings algorithm? Clark-Weight is classical heuristics for solving VRP. Some of the advantages it offers are efficient for routing problems, merges route based on distance savings, reduces total travel distance, naturally builds multiple feasible routes. The key idea is to combine two routes if it reduces travel distance and satisfy the time constraint. Basically, what it means is that if I'm traveling to, let's say, a location B in one day and location C in another day, and if I can combine visiting A and C in a single day, and the total travel distance reduces, and the travel time lies within the time constraint of 14 hours, I will just combine them and put them in one day. So why not traveling salesman problem? So TSP assumes one single route, visit every location exactly once, return to the starting point, no route constraints. But in our problem, you cannot visit all relatives in one day. There is a strict time limit of 14 hours per day. Multiple routes are required across multiple days. Therefore, TSP does not model multi-day delivery constraints. Conclusion for algorithm selection. Our problem problem involves a single depot and multiple destinations. Each location must be visited exactly once. Routes start and end at the depot. Each route has maximum duration constraint 14 hours. Goal is to minimize the number of route days. Because of the above constraint, it fits vehicle routing problem rather than TSP. Therefore, Clark-Weight savings algorithm is a suitable approach to efficiently construct delivery routes. P versus NP. VRP is known to be NP hard and its decision version is NP complete. Therefore, not known to be solvable in polynomial time. Solution search grows exponentially. The idea is to initially assume I visit each relative in one single day. So I start from home, visit relative A and come back to home like that. So each house is its own day. Compute savings. Savings algorithm is computed as follows. Savings of I comma j is the distance between home and relative I plus the distance of home and relative j calculated using Euclidean distance minus the distance between I and j. So if visiting I and then j in the same day saves distance and merge them, but merge only if the total time is less than 14 hours. So the pseudocode for it is create initial route. Each relative has its own route, home, RI, home. Compute savings for each pair. Sort the savings in descending order. So I can merge the highest savings first. For each pair I and j, if routes containing I and j can be merged and time constraints satisfy, merge routes. Stop when no more merges are possible. Output final routes. So step one is to build a graph from input data set. So I receive input a set of a list of coordinates for each relative. So the nodes will be each of the relatives. The edges will be the distance between every pair. Weight will be the Euclidean distance between each pair. This forms a complete weighted graph. A Euclidean distance calculation is calculated using this formula: root of xi minus xj the whole square plus yi minus yj the whole square. And as we know, time is a distance by speed, and I need to maintain a constant speed of 40 units per hour. So daily working time 8 a.m. to 10 p.m. total 14 hours. At each house I spend 15 minutes. So the total route time I should also take into account the 15 minutes I spend at each house. So travel time plus visit time should be less than or equal to 14 hours. Savings constant concept I mentioned earlier. So example savings is home A, home B, home. Total distance will be this. And then because it is less than 14 hours, I can merge it into a single day. So home A, B, home, and the savings will be represented as S of A, comma B. So higher the savings, the better merge the candidate. That's why we are sorting the savings list in descending order. So start with one route per relative, compute savings for every pair, sort savings descending, iterate merge route, check time constraint before merging, stop when no valid merges remain. So initially day 1 home A, home, day 2 home B, home, day 3 home C, home. So in this the days reduce from 3 to 2. So this is input data. We assume a 2D map grid, kilometers in units, and these are the relatives location represented in a graph. So I calculate the distance matrix using Euclidean formula. This is the matrix. And initial routes, I assume each relative to be visited in separate day, and total will be 62.4 kilometers, and it will take 5 days. And this will be the route. But then I calculate the Clark weight savings and sort it in descending order, and then I merge it, and after merging the route becomes 2 routes, so I can complete it in 2 days instead of 5 days, and the final distance will be reduced to 33.47 kilometers, which is approximately 46% improvement from the original time. And this becomes the origin 2 days from E, F, A, B, and then back to home, from E, C, and then back to home. So the savings computation is big O of n square. Sorting savings is n square log n. Root merging takes a complexity of n square. Overall complexity becomes n square log n. Advantages: efficient heuristic solution, reduces number of travel days, works well for medium-sized routing problems, simple yet powerful algorithm. Limitations are not guaranteed to be globally optimum, assumes constant travel speed, real road networks may differ from Euclidean distances. So alternatives I consider a traveling salesman problem. It is not suitable because problem requires multiple roads or days starting and ending at the depot. Genetic algorithm or meta heuristics, they introduce high computational complexity and randomness. This is unnecessary for structured routing scenario. Branch and bound exact method provides optimal solution but become computationally infeasible as the number of location increases. The project demonstrates modeling a routing problem using graph theory, applying Clark-Wright savings algorithm, optimizing delivery routes under time constraint. Outcome: minimum number of days required to deliver invitations. Future improvements include using real road network distances instead of Euclidean distance, considering traffic conditions, applying meta heuristic like genetic algorithms or tab search, scaling the model to hundreds of delivery locations. Thank you.